Okay, so this is our last section before the exam. Hopefully everybody found those questions I put up for Monday. I got a couple confused emails. Did people find those? Okay, I still will put up a practice exam for you. A few more conference disasters that I had to deal with than expected, but those should go up this evening or this afternoon, so you'll still be able to use those as usual. So today we're going to go through a couple of topics that I'm going to be hopefully really clear about what I want you to take away. And hopefully, this will go a little short. Okay. So when we left off, we had one of our types of movement across the walls of the nephron that we hadn't got to yet, and that was excretion. Really, this is kind of an exception to our other types of movement. So when we say excretion, we really just mean what we're urinating out. So there are a couple ways we could measure this, or ways we could talk about it. We could talk about the excretion rate, so like how much per minute. We could talk about clearance, which like the basic idea of clearance is like how much blood are you cleaning is the way I like to think about clearance. And then we have excretion, which you've looked at on that worksheet before, but that's basically just the physical control of urination. We could calculate out excretion rate, but really what we want to focus on here is to realize that when we're looking at the contents of urine, when we're looking at what has been excreted, this can help us figure out what's going on physiologically in the kidneys, because we can use it to sort of calculate backwards whether we have net reabsorption of a substance or net secretion. So excretion rate is basically the amount of the substance excreted, so the amount coming out in the urine, right, is going to be equal to the amount that you filtered. So how much came out with the plasma as you moved the contents of the plasma, the fluid, and the solutes into the nephron, plus the amount you secreted. So that's anything that came from the plasma and went back into the filtrate, minus the amount reabsorbed. So this is saying, right, excretion equals the inputs into the nephron. So the inputs are the filtration plus secretion. So both of those go the same direction into the nephron. Minus reabsorption. So that's what we moved from the nephron back into the blood. Okay. So if we know the excretion rate, so we could measure how much of something is in the urine. And if we can measure how much is being filtered, which we talked about when we talked about glomerular filtration rate. So this would be like your filtered load, which was basically the concentration of a substance in the plasma multiplied by the glomerular filtration rate. So like how much plasma is getting filtered through the kidneys. So these are two things we could measure with like a urine test and a blood test. If we can measure these two things, we can then figure out just like, are we secreting more of this substance into the blood, or sorry, are we secreting more of this into the kidneys, or are we reabsorbing more of it into the blood? So that's the basic idea here. Is just to figure out from these two things that we could measure what's happening in the kidneys. That's the basic idea here, so it should not surprise you that that is the type of question you might get on the exam. I tell you something about how much is being excreted relative to the filtered load, so how much was getting into the nephron. You should be able to compare those two. You're peeing out more than you filtered in. You had secretion, right? Because that stuff has to come from somewhere. If you are peeing out less than you filtered in, then that substance still had to go somewhere, so it got reabsorbed back into the blood. So that's the basic question type. Shouldn't involve any complicated math. I think understanding this from a conceptual level is probably honestly easier than memorizing the equation. It's just realizing that when you compare these two numbers, you can figure out whether you had to put more in or whether you took some back to the blood. Questions about this idea about excretion? So this bit on clearance is really just so you have heard this word if you're in a clinical setting in the future. Clearance is something that is talked about clinically. It's kind of a theoretical idea of like how much of the plasma has been fully cleaned of this substance, although we know because of transport maximums, that's not really how the kidneys work. So if you wanted to calculate clearance, you would divide the excretion rate, so how much of this substance is coming out in the urine per minute, by the plasma concentration, which you could measure with a blood test. And that would give you a rate of how much blood is kind of being cleaned. I'm not going to ask you to calculate this, but I don't know what comes up like next in your future nursing classes or in any future clinical classes. So if they expect you to know about this, I want you to have at least heard the word. So that's why this is in here. So we might point out one thing that we have focused on, glucose. I would say this is probably the most important thing here. You should not have an excretion rate of glucose if your glucose levels in your blood are appropriate, right? You should be reabsorbing all of it. So your excretion rate should be 0, right? So that's why the clearance rate of glucose is 0, because you're dividing 0 by some plasma concentration. So if you have a clearance rate of glucose that is not 0, that means something's going wrong. So Excretion, you drew a flow chart on that worksheet. So we don't really need to go through it again, but I'll just emphasize the takeaways since they're on the slides, right? So this is just another word for urination. Hopefully you understand the pathways either from anatomy lab or from looking at these diagrams. That after we form the filtrate in the renal tubules, we do all of our secretion, we do all our reabsorption, we now call it urine. So it flows down from the ureters into the bladder, where we can urinate it out. We're storing it until we excrete it, which has to do with sphincters. So basically, your bladder can sense how stretched it is. There's an internal urethral sphincter that's not under your control. So at a certain amount of urine, it's going to open up. There's another external urethral sphincter that you do control, although there is an amount over which you can like overload it. You should be able to control the external urethral sphincter and hold your urine in. So that's basically the big takeaway of this giant block of text. All right. So our last topic is about sodium balance and potassium balance, okay, both of which kind of happen at once. So if you remember our sodium potassium pump, right, we're pumping sodium and potassium in opposite directions. Remember when we were looking at neurons, right, we had sodium flowing in, we have potassium flowing out. So often sodium and potassium are kind of the reverse of each other, and that's going to be true in the kidneys as well. Okay. We have words that we can use for this. So when you see the words hypernatremia or hyponatremia, look for that Na in the center. That tells you we're talking about sodium. Right. Emia should signify to you we're talking about blood, and then hyper and hypo are always just telling you high versus low. So hypernatremia is high plasma sodium. Hyponatremia is low plasma sodium. So these are things you could measure in the blood of a patient. So sodium is the primary solute in the extracellular fluid. So sodium is the thing we talk about a lot when we're talking about solutes, right? We talk a lot about the direction that sodium moves. We've talked about sodium-potassium pumps kind of throughout our different units. Sodium is important for normal osmotic pressure. So for controlling which direction water is going to move, that often is going along with regulation of sodium. And it's also important for excitable cells, by which we mean nerves and muscles, basically. Right? So the function of those action potentials depends on a specific concentration of sodium in the fluid surrounding the cells. So that's why we care about sodium balance. We want to make sure that we keep those concentrations of sodium in the blood consistent within our tolerated range so that we don't mess up the movement of water retention in your body, so that we don't mess up anything about how your nerves and your muscles are working. So we can think about what is happening to sodium in the different parts of the nephron. So sodium is freely filtered. All that means is there's nothing blocking it from coming in out of the glomerulus and into the Bowman space, and therefore into the nephron. So it's going to be coming through with the water, with some of our other solutes, with the glucose. It does get reabsorbed. So we're reabsorbing about 70% in the proximal tubules. So kind of like our water, we're reabsorbing a lot of sodium as we go through that first part of the nephron. It's also going to be reabsorbed in our distal tubules and our collecting ducts, which, if you remember back to our discussion of how water works, where water is reabsorbed, you might come to suspect correctly that that's where we're going to be regulating it. A mass reabsorption of things, so like reabsorbing a lot of it, usually happens in the proximal tubules, whether we're talking about the solutes or we're talking about water. And then the regulation is kind of a fine sort of fiddling, a fine tuning at these distal parts of the nephron. Sodium doesn't get secreted, so we're not going to take sodium from the plasma and push it back into the nephron. And the hormones that are going to be regulating the reabsorption of sodium and also potassium are aldosterone, which is probably the only one I'm going to ask you to learn about today, but there's another one, A&P, and I really just think about these as doing the opposite of each other. So whatever we say about aldosterone today, A&P is just the hormone that would do the opposite thing. So this regulation, when we say regulation, what we mean is we're responding to some type of cell signal. In this case, we're responding to a hormone. So it's going to be regulated in these cells called principal cells, which we find in the distal tubules and in the collecting ducts. When we think about reabsorption of sodium, we might say it's active. So remember, active, when we say active, we're saying something slightly different than when we say regulated. When we say regulated, we're talking about responding to a signal, like a hormone. When we say active, we're saying it takes energy. So all that bit about active reabsorption means is that the sodium potassium pump uses ATP. So we have to use energy to do this reabsorption. So here we see a picture of a cell. So this is a cell we have seen before, and we've seen possibly this exact diagram before. So what we're looking at is the proximal tubule. So that's the first part where we have the unregulated reabsorption, but there's a lot of it. So what's happening here is that we have a sodium potassium pump that's affecting the sodium gradient. It's creating a gradient where we have low sodium in the cell. So sodium wants to come in, and then it gets pumped out by that pump, which is why this is active reabsorption, because that requires energy. So that goes through back into the plasma. That's really the big takeaway from this slide, although there are many other things on it. This is what's going on in the distal tubule. So we will talk a little bit more about the distal tubule because we are going to see how this gets regulated as well. But right now we're just looking at an epithelial cell, which is not one of the cells where we have a response to the hormone. So we see that in some of the cells, a similar thing is happening. We have sodium and potassium pumps. We have sodium coming in towards this low sodium region that we've created, and then moving into the plasma. So the issue with the gradients is kind of the same here. A difference we might look at, although potassium is usually kind of a tack-on topic, much like A&P being the opposite of the hormone aldosterone that we're going to talk about. Potassium is kind of doing the opposite thing as sodium. So there is secretion of potassium in the distal tubule. So that's the main thing that if you were focusing in on differences between the two, that is the one I would look at for the epithelial cells. All I would ask you about from the stuff on the exam is whether we're going to see regulated reabsorption in a region, so either in the proximal tubule, which is unregulated, or in the distal tubule and collecting duct, which is where we are going to see regulated reabsorption. That's pretty much it. So that's understanding what process is happening in different parts of the nephron. Okay, so that gets us to how the regulation is happening. So when we talk about the hormone aldosterone, its effect is that it's increasing sodium reabsorption. So increasing sodium reabsorption, it's making it possible for more sodium to move back into the plasma. In terms of where it's come from, it's coming from your adrenal glands, specifically from the adrenal cortex, which we have a lot of hormones we're interested in are coming from the adrenal glands. So we talked about cortisol in previous units. We talked about how the adrenal medulla secretes epinephrine in response to the sympathetic nervous system. So if you ever think about the adrenal glands in future in detail, really cool how they produce lots of different hormones. They're important for this reason. Okay. So what aldosterone does is that it's going to increase the number of sodium potassium pumps. Okay. The sodium potassium pumps are on the basal or basolateral side of the membrane, aka on the side where we have the blood. That's all that basolateral means. Okay. So sodium potassium pumps, we have more of them when aldosterone is present. The other thing it's going to do is it's going to open up more sodium and potassium channels on the apical membrane. So all this is basically doing is making more doorways for sodium and potassium, right? So the job of our sodium potassium pump is to maintain this gradient so that we have like a pull on sodium. Since we are making sure we have a big pull on sodium, we're opening up more channels so that more sodium can get in. So that's how it's working. You have aldosterone present in the blood, you get more sodium potassium pumps, more sodium channels, so that you can have greater overall movement of sodium into the blood. Questions about this process? I'm sorry that the text on this figure got kind of scrambled. You guys said that the text usually in the figures looks okay on your slides. Is that true? Hopefully you have a good picture of that. So this is pretty similar to what we saw when we talked about water balance at the beginning, right? So we talked about how ADH is increasing channels for water on the apical membrane. Aldosterone is regulating sodium and potassium, increasing the number of channels for sodium and potassium, with the added bit that we need to maintain that gradient. So it's also increasing sodium and potassium pumps. So like conceptually, it's doing the same thing. Question you might see for the exam. Okay, what hormone are we talking about when we're talking about solute reabsorption? Sodium reabsorption is really what I mean here. Although it does also have effects on potassium kind of as a byproduct. And then we might want to know the effect of aldosterone on those principal cells. Those are the cells we just looked at where the regulation is happening. Has to be on principal cells in the distal tubule and the collecting duct because that's where we see those cells. And the effect is just more reabsorption. pretty much. More reabsorption. All right, and it does that by having more channels. And they're on the apical side, so just the side facing the urine. And more pumps, so more ATP pumps. More sodium, potassium pumps, or ATPase. That protein has a lot of different names. The questions about this, the overall way that aldosterone is working on these cells. So finally, I'm sure this will also come up in your future classes, so we do want to mention it. There is something called the renin-angiotensin-aldosterone system, or RAAS, which works a lot like our clotting factors did, kind of. So what this system is basically we just have kind of a domino effect of these different hormones. Okay. The RAAS system is that we have hormones that are affecting the production of other hormones and then converting more hormones, so that we ultimately end up with aldosterone that can regulate our sodium reabsorption. So this is how we're controlling the production of that aldosterone and thereby controlling whether we're reabsorbing sodium. So there is a lot of text here, but I'm going to kind of simplify it, which is just that renin gets secreted by granular cells in the juxtaglomerular apparatus, which you looked at. So renin is being secreted by those cells sort of in the late distal tubule that are right next to the glomerulus. So you can guess that they're going to be responding to what's coming out in the urine, right? Kind of like we regulated the GFP and the GFR, regulated the glomerular filtration rate by sort of sensing the flow rate there. We're going to sense the contents of that filtrate flowing past, and then that's going to help us decide whether we want to reabsorb more sodium or not. So once we secrete renin, I'm going to skip some of these steps because they're kind of details. So the next thing we're going to do is we're going to make, let's call these both number 2. So the liver has been making something called angiotensinogen. When you saw this inogen ending on some of our proteins when we were talking about clotting factors, you might remember that those were the ones that needed to be activated, so they weren't working yet. So the liver is making this molecule that gets converted into angiotensin 1. Okay, so renin converts this precursor molecule into angiotensin 1. And then number 3, angiotensin 1 gets converted into angiotensin 2. And then number 4, that tells us to make aldosterone. Our kind of pathway that we would pay attention to is renin to angiotensin 1. To angiotensin 2. To aldosterone. Okay. That's kind of our workflow here. So there are other molecules involved, as you can see from the pieces I kind of skipped in this pathway. So there are enzymes in the walls of the capillaries that help us to convert some of these substances to finally stimulate our aldosterone production. But basically, this is all a response designed to make aldosterone when we sense things about the contents of the urine and produce renin. Right, so that's kind of our start point and our end point. So here's just a picture of what would be happening from a sort of more anatomical perspective, which is that our liver is making this precursor molecule. Then when it bumps into renin, it turns into angiotensin 1, which has to bump into the walls of the capillary where we have our ACE enzyme, turns it to angiotensin 2, and then the adrenal gland makes the aldosterone. So that's just with some of those details on there showing us how that would physically work. What I would like you to take away from this is that the ultimate effect here is going to be a rise on blood pressure, a rise in that. So what's kind of happening here as we are increasing our aldosterone secretion, right? One of the things this does, if we increase aldosterone secretion, what we're saying is that we're increasing the reabsorption of sodium. If we then think about from the perspective of the blood, the perspective of the plasma, now we have this plasma which has a higher concentration of solutes. Right? We know that a high concentration of solutes exerts a pull on water. So when we increase the reabsorption of sodium, ultimately we're having an effect on water reabsorption. So we're ultimately increasing the volume of plasma, the volume of blood in our arteries, in our cardiovascular system. So that's kind of why the system exists, is ultimately it's a regulatory mechanism to adjust mean arterial pressure, so to adjust blood pressure. And when we talk about it, we're talking about the nitty-gritty of like, where is the sodium moving? But when you think about a patient or a person, what really matters for us is the effect here on the blood pressure. So from this map, you can see that it's happening at the same time as our water balance stuff is happening. So at the beginning, we talked about ADH. Make sure to tell the difference between ADH and aldosterone when you're studying. So that's our antidiuretic hormone. Right? Our antidiuretic hormone was directly increasing water reabsorption on its own. But this aldosterone business affecting the sodium reabsorption is kind of adding on to that, right? So it's also working in concert with our water reabsorption due to ADH secretion, all of them raising our blood pressure. Okay. So these three are just how we would release renin, right? So remember renin, we have our angiotensin 1 and 2. In that order for once, 1 and 2, ultimately gives us aldosterone. Right, that was from our previous slides. Our ultimate goal for increasing sodium reabsorption. Why we want to do that is because we want to increase blood pressure, right? So that's the ultimate effect of this RAS system. So the stimuli for the release of renin at the beginning here are going to be signals that tell us that we've had a drop in blood pressure, right? The whole goal of this system is to raise blood pressure back up. So if we sense anything that tells us we have low blood pressure, we're going to start releasing renin. So ways we might know from the kidney perspective that we have low blood pressure. So we might sense decreased pressure in the afferent arteriole. So that's the blood coming into the glomerulus, coming into the kidneys. I'll mute that. Okay. So blood coming into the kidneys, into the nephron through the afferent arteriole. That has low pressure, right? That's part of our cardiovascular system. If that has low pressure, that's a signal that maybe we have low blood pressure. Renal sympathetic nerve activity goes back to our baroreceptor reflex from the cardiovascular system. That's just another thing that is kind of a response to low blood pressure. So that's just another signal for low blood pressure. And decreases in the sodium and chloride in the distal tubule filtrate is another signal of low blood pressure, basically. I'm going to just kind of circle all of these, right, and emphasize that this is low blood pressure. So we're going to say low, I'm going to be more scientific than that, mean arterial pressure. So anything that's telling us that we have low mean arterial pressure means we're going to raise mean arterial pressure, means we want more aldosterone, more sodium reabsorption. So we have to release renin in order to make that happen. Okay. So my question for the exam would really just be, what is triggering the renin release? What are we responding to, right? Like, why are we releasing renin? Why do we want to make aldosterone? The answer to this is low MAP, low blood pressure, or any of these factors that might tell us we have low blood pressure. So this is a corrective mechanism to fix low blood pressure. So we can see that in our flow chart form. If anybody likes these, I think I've heard more people complaining about these and disliking these than enjoying these, but I kind of like them. So hopefully one or two of you like them. So this is just telling us, right? Low mean arterial pressure creates signals throughout our body, right? So anywhere we have cardiovascular system, we're going to have low pressure. In this case, afferent arterioles are directly in our kidneys, directly near these cells that can respond to it. We'd also have a low glomerular filtration rate, right? So low rate of plasma getting filtered into the kidneys because of this low pressure, which means that not as much sodium and chloride got filtered into the tubules because not as much plasma got into the tubules. Okay, so that's how that sodium and chloride fit from the previous slide with 3 factors is related to this. And then the baroreceptor reflex has increased sympathetic activity. So these are all just telling us we have low mean arterial pressure. So we release renin to fix it. Renin ultimately increase aldosterone, increase sodium reabsorption, increase water retention. So those are the parts that might be on the exam. I'm going to say these last couple of things so that we don't have to put them onto the next exam, but this is just kind of for your future information and understanding, because I do not know what will come up in your future classes. When I said A&P natriuretic peptide is the opposite of aldosterone, basically what I mean is that it's secreted when we sense high blood volume, which is linked with high blood pressure, right? And it does that because this is a hormone that's secreted by the heart. So that's kind of cool, right? That the heart secretes a hormone. So that's why it's called atrial natriuretic peptide. Actually the atria of the heart. Okay. So what A&P does is it decreases sodium reabsorption, right? Because it closes sodium channels. That's the way in which it's the opposite of the aldosterone. The overall effect is that because we've closed those channels, we're not reabsorbing as much. We are increasing the sodium excretion rate. Okay. Right, so if we don't reabsorb it, we got to pee it out. So here's kind of how that flow chart would work. So we can see it's just doing the exact opposite. It's turning off this RAS system. So this is one of those cases where throughout A&P, right, we've had things that do like kind of opposite triggers, right? We had our insulin and our glucagon doing opposite things. We had our sympathetic and our parasympathetic doing opposite things. Sodium and potassium doing opposite things. This is just another case of that. aldosterone and A&P do opposite things. Again, probably not going to put this on your, no, I am not going to put this on your exam because I think I gave you enough example type questions, but you just may see these words in a clinic at some point in your life. So potassium balance also exists. It's pretty much the opposite of sodium balance. So hyperkalemia and hypokalemia are basically things you could notice in the blood that are indicative of kidney problems. So look for the K in the middle to tell you we're talking about potassium, the emia part to tell you we're talking about blood, and then the hyper and hypo to tell you we're talking about high and low. Potassium is also important for our excitable cells, right? Potassium was one of the other ions that we talked about when we talked about the action potential in neurons. So we see a similar sort of pathway. The only real difference here is that potassium is moving in opposite directions and it can be secreted. And then we got hormones affecting it. Short, which I don't know, 10 minutes before the end of class really counts as short, but questions leading up to our exam on Friday? No, we'll do that next one. Yeah. I think this is plenty. Really short unit, but I am of the philosophy that it's kind of hard to remember things from before spring break, after spring break, and I think Easter break may be the same. So that's why we kind of sandwiched a whole unit between the two. Okay, cool. Well, I'll stick around, but we are done. I'll put up a practice exam as soon as I can, and good luck studying and email me with any questions.